Hey everyone, this is lecture 9, and in general it's about estimation, but let's focus this one on a tiny topic, tiny but important, on maximum likelihood estimation. In this one, we will only talk about small idea of independence, well, small idea with large implications, and then about the core, the heart of this lecture, parameter estimation via maximum likelihood estimation. Let's go on. Independence. Well, the issue of independence, or the definition in probability, at least statistical independence, is defined as follows. If you have a joint distribution of two variables and it factors in the product of their marginals, then x is independent of y. The variable x is independent of variable y. An implication of independence, or sort of another definition, is that conditional distribution of x conditional on y is the same as marginal of probability of x, marginal distribution of x. So both of those statements, equations on top, mean that y and x don't contain information about each other. That's basically all it says. Well, it's clearer in the bottom line, right? Basically, it says no matter what y is, no matter what we say the value of y, or set the value of y to, probability density or probability distribution of x doesn't change. It was probability of x before, and it is still probability of x after. And yes, observing y does not help predicting x. But the same is true as well. Observing x does not, the converse is true. Observing x does not help predicting y. For example, independent events. Winning on roulette this week and next week. They're independent. Independent is Russian roulette. So what we see on the left are non-informative variables. The joint distribution is just the product of marginals. X and y. If you know value of y, the distribution of x doesn't change. It is the same for any value of y. The distribution is the same. But here on the right, the variables are dependent. Yes, if you know that value of y is 0, you don't know much about x. It could be anywhere. But if you know that the value of y is 2, then you pretty much know where the x will be, or you can identify the x. So there is a dependence between the value of x and the value of y, or there is, each of them has a predictive power about each other. Of course, depending on what this value is. And better in these two examples illustrated with the conditional. This holds for this joint, but it does not hold for this joint because knowing y does change x. Some more interesting points is conditional independence. So when we talk about pure independence, it's whatever the variables we observe. But when we talk about conditional independence, we're talking about probability, joint probability of x and y conditioned on z, whether it factors into conditional distribution of x given z or conditional distribution of y given z. If it does, then knowing z makes x and y independent. That means, again, this will not hold, but conditionally they are independent. And again, z is a common factor if we draw this graphically, and both x and y depend on z. But if we don't see z and only observe x and y, then they are not independent. There is information in x about y and in y about x. And that information, this bit, is whatever z is adding into x, or whatever z is adding into y. So for example, dependent, shoe size and reading skills in kids, right? There is a clear dependence and we can measure that. Shoe size, the larger the shoe size in kids is, the better the reading skills are. And that's a strong relationship. You can always rely on it. And converse as well holds. If the reading skills of a child are quite good, that means the shoe size will be larger. You can count on that. I mean, it's not a deterministic relationship, but the probability is very high. Well, let's look at the common cause, or the variable that causes both of them, or that they are both conditioned on, is the age. Shoe size and reading skills given the age. If we know the age of the child, or if we fix the age, then there is no dependence. Well, the point here is, of course, the older the child, usually the better they read. And so once we know the age, or if we fix the age, say, I don't know, 4-year-olds or 7-year-olds, and within that fixed age, we compare relationships between shoe size and reading skills, there won't be any. Another example. Again and again, scientists analyzed the data and looked at it, and they could confirm with highly statistically significant correlation, p-value way less than 0.5. Correlation exists between stork population and human birth rates across Europe. What else do you need to have a proof that storks deliver babies? That's total truth. That's absolutely correct. That's what the data tells us. More storks, more babies. No one can argue with this. Until you realize that you forgot to normalize by the country size. You just look at every country and look at population of storks in each country and look at how many babies are in each country. And of course, the larger the country, the more storks and more babies. So those are examples of conditional dependence. In causal learning, something aside, for this class. In causal learning, we call common causes. We call Z variable a common cause of X and Y. And when you fail to observe common cause or fail to account for it, then there is unexplained correlation between X and Y. Or you create an explanation for it yourself, as storks deliver babies. Another example of conditionally independent events: London taxi drivers. A survey has pointed out a positive and significant correlation between the number of accidents and wearing coats. They concluded that coats could hinder movements of drivers and be the cause of accidents. A new law was prepared to prohibit drivers from wearing those coats, until people realized that people wear coats when it's raining. And when it's raining, the roads are slippery and there are more accidents. So that's another good one. Because correlation does not equal causation, like this XKCT comment wittily points to us. I used to think correlation implied causation. Then I took a statistics class. Now I don't. Sounds like the class helped? Well, maybe. The point being, correlation doesn't have to imply or does not imply causation, but it doesn't preclude it either.